All right, I mixed up some epoxy and let's save that. Glued the little corner on that busted off. I don't know which one it is now. They're all cracked. I think I glued that one on. Well, maybe not. Anyway, it doesn't matter. Let's see. So what I'm going to do is I'm going to try to calibrate this thing. I've got the procedures here. It's a whole bunch of procedures. And there's two different sets of procedures. One for serial numbers 20,000 and up. And we have 141,000. So we are 20,000 and up. So this is the location of the knobs to turn. And here is the whole procedure. So procedure, serial numbers 20,000 and up. Reference current adjustment 13.6 volt. Connect the digital voltmeter to the low lead input. Ground and connect the high input to TP1. Okay, so we need to get this thing all ready for adjustments. All the adjustments are on the top, so I'm gonna flip it sideways. I can make it easier. Flip it sideways. All right. Where's my? Here it is. So people were wondering what this weird thing is. They may have seen it in the video. I made a shim that's exactly the right amount. When you plug this in, it droops just a little bit because when it's inside the card cage, it's elevated. It's not flush here. There's an actual gap here, and this is calibrated for that gap, so you can put this under there. So anyway, it just keeps it up a little bit. All right, so we will get a voltmeter here, and it says, let's see here, test point 1. Test point 1 is way over here. All right, test point 1. And I think it said this, the output. I think it just said the output, so we will stick it here on the output. All right, connect the digital voltmeter low lead to the ground at the negative end, at the negative end of C400. C400, I guess, is probably that big capacitor right there. So we will put our ground there. All right. And let's turn the power on. And we're measuring 14.5 volts. And we should be measuring 13.8. So we want to adjust R400. R400. Oh, this is hard to read. For sure it's that one right there. Yep. 13.8. It is very sensitive. 13. Okay, 13.82. I would call that good. 20 volts supply. Move the digital voltmeter high to test point 3. Where's test point 3? Test point 3. Test point 3 is over here somewhere. There's the cap. Oh, there it is. It's hiding. Test point 3. Okay. Test point 3. Adjust 415 for 20 volts. We're measuring 19.968, which is probably pretty good, but we can tweak it a bit. 415 is that one there, which is hard to get a screwdriver on because the test things are in the way. Guess I could just kind of grab it. See if this is, oops, that's going the wrong way. There we go. All right. 19.999. I'll call that good. Okay. 17 volts. Move the high lead to test point 8. Test point 8. Test point 8 is way over here. Okay. Test point 8. It is measuring 16.9. This will be 17. Check for a plus and minus 2 point. Yeah, so it's fine. There's no adjustment. It's just check. Okay, then we want to move the test point 9. And we are measuring minus 6. Yeah, same thing. So we're checking out just fine there. Disconnect the voltmeter. Okay. Voltmeter's disconnected. Adjust the square wave high frequency compensation. Oscilloscope. Connect the output through a 50 ohm coax cable to a 50 ohm termination at the oscilloscope vertical. So they want me to put a, okay, want me to put 50 ohms at the oscilloscope. I can do that. Okay, and the output. All right. Okay, through a blah, 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 blah. Check that the display amplitude is at least 10 volts. Let's see, we want to have function square wave. Okay, function square wave. Okay. And we want to have multiplier by 0.4, 3, 4, and frequency is 1 hertz. All right. I'm going to set the vernier to number 1. Okay, so oscilloscope should be at 2 microseconds per division. 2. Okay, 2 microseconds per division. Volts per division is 2. All right. 2, okay. DC coupling, connect, check the display for at least 10 volts peak to peak, and we are not getting 10 volts peak to peak. We need to turn up the, let's see, fully clock, oh, amplitude fully clockwise. Okay, yes, we're getting 10 volts. All right. Set the oscilloscope variable volts per division triggering intensity for a visible, vertically centered square wave high frequency compensation for a square front corner flat top. Okay, so we're kind of adjusting it like we would a oscilloscope probe. Set the time base to 20 nanoseconds. Okay, 20 nanoseconds. Okay, looks pretty good. Measure the rise time of the leading edge. Okay, I just push a button now. Add vertical, horizontal rise time. Okay. Rise time we're getting 55 nanoseconds. Should be 100 nanoseconds or less. We're getting 55, so everything's good if necessary. All right, dial calibration. Function triangle. Function triangle. Okay. Let's go back out. See what it's doing. All right, function triangle. Okay. Time base 10 microseconds. Okay. 10 microseconds. All right. Trigger display. Set the frequency dial to the point near 10. Set the frequency Hertz dial just to the point near 10 where the frequency of the displayed waveform becomes maximum and there is not further change. That's interesting. Okay. Am I missing something here? I think so. I don't know, it looks okay to me. Okay. Check that the frequency reads 10. If the dial does not read 10, loosen the 2 set screws on the brass connector. All right, I don't think we need to do any of this. Let me put it on 10. It's just making sure that the potentiometer is clocked right, and it is. Okay, one-time symmetry adjustment, control settings, square wave, function square wave. Okay, function square wave. Okay, frequency Hertz near 1. Okay, near 1 Hertz. Symmetry. Okay. Oh, let's see. Set the oscilloscope to display 1 full triggered square wave cycle over 10 graduations. Okay. About there. Yeah. Yeah. Okay. Adjust R45 so that the positive going and negative going portions are of equal duration. Oh, okay. Okay. They look like they are already, so I'm not going to touch it. They look fine. Disconnect the 50 ohm resistor on the oscilloscope input connector. Okay. Times 10 calibration. Use an oscilloscope. Multiplier times 3. Times 2 times 3. Frequency Hertz 10. Okay, I gotta go over here to 10. Okay, function triangle wave. Triangle wave, there we go. Function 1 Hertz. What? Wait a minute. Frequency 10, yeah. Function, counter, oh, counter. Frequency 1 Hertz. Clockwise force 0. Connect. Time base, counter reading of. Okay, so now we're going to calibrate the time, and we need to go into a counter. Okay. Okay, I have the counter hooked up, so now I can tweak R20. And, oh, it is a little sensitive. Okay, 10, there we go. 10.0005, I think that's pretty good for this thing. Okay, so we have that done. ×1 calibration, control settings 1. Okay, I gotta go back to 1. I can just go this way, okay. Okay, 1. Time base 1 milliseconds on the scope. Connect T connector, connect input counter, T connection, counter reading. Yeah, I don't really need it. Okay, so just ×1. Oh, I see what we're doing. Okay, well now we need to figure out where R38 is. So we calibrated it with the dial set to 10. Now we're going to calibrate it with the dial set to 1. So it's kind of like a slope and offset type of deal. All right, so we need to figure out where R38 is. Pretty sure it's that one there. Yeah. Okay, so we can adjust this one. Oh, wow, it's real touchy. Real touchy. 1.03. Oops. 1.12. It bounces back when you have to go lower than you think, and then it'll come back. Oh, there you go. 992, 993, 994. Oh, geez. Now it jumped to 995. Let me adjust the dial. Oh, yeah, it's very sensitive. That's good. Okay, so we got the 1 set. Check the counter reading of 10. Oh, they're interactive, so you have to go back to 10. Make sure it didn't move very far. Okay, let's go to 10. Yeah, close enough. That worked out good. Okay, now ×5 adjustment. Multiplier to 5x, or 10 to the 5th, okay. 10 to the 5th. Frequency 10 hertz. Okay, I've got to go to 10. Which is where we are. Okay, ×5, 10. Function. Adjust for a counter reading of 1. Okay, we're at 1.025 right now. Okay. So we need to adjust C190. Okay. I think there's only one. Oh, there's a couple C's on there. C190. C190. I think it's that one down there. C190. Okay. Let me get a insulated adjuster and see if this is doing anything. Oops, yep. Had to break it loose. Oh, there we go. There we go, perfect. Okay, we've adjusted 190. Where am I? I've lost myself. I got lost. Oh, there we go. 190. Okay. Now we go to the 1 setting. Okay, now we set it to 1. .02. Okay, so now we adjust C79. Where is C79? C. Might be that one. I think it's that one. Oops. Okay, let's go to 10, make sure it hasn't moved. And it has. Okay, I'll go back, just the other one. Now go to 1. And that's good. All right, we'll call that quits. All right, so we've done the back and forth there. Now we need to go to below. Okay, we don't need to do that. Upper wave and lower wave adjustments for, all right, function sine wave. I think we now need to have the oscilloscope hooked back up again. All right. Multiplier on 10. Connect to the distortion analyzer through a 50 ohm coax cable. Adjust for a minimum distortion as read by a distortion analyzer. Okay, we will use our Keithley. It has distortion analyzer built in. THD. We will go to sine wave. Okay, sine wave on times 10 clockwise. Multiplier frequency 10, 100 hertz. Okay. Okay. 100 hertz. Underflowing phase is in. Offset is in. We are underflowing our total harmonic distortion. Adjust the upper and lower for minimum distortion. I'm not measuring distortion yet, though. Let me look at this on a scope. Oh, is that good? That's on, that's on. I'm not getting any output. Why am I not getting any output? Oh, there we go, I got output. All right, okay, we're getting output, and it's healthy. Put it in the Keithley, and we're getting underflow total harmonic distortion. Underflow. Oh, there we go. Okay. All right. Oh, yeah, we need at least 20 hertz for the yeah, we need at least 20 hertz, not 10. Yeah, that would be good there. All right, we're measuring 0.19 total harmonic distortion. And adjust R150 and R170 for minimum distortion. That's the upper and lower portions of the sine wave. Okay, R150 is that one, and R1, what did I say, R170? R170. So it's these two guys there. We need to adjust those from minimum distortion. Okay. Oops. They're a bit tricky. They are very tricky. Oh, there we go. It's very finicky. Very finicky. Adjust this one, that's too big. Go this direction, it's getting smaller. No, it got bigger. Okay, about there. I think it was actually adjusted probably pretty good. Oh, there we go, 0.1. No, that's not bad. Oh, there we go, 0.2. Okay. Let me adjust this one. See if I can make it better. Oh, this is really hard to do. Well, there we go, 0.15. Oh, it's flickering, it's flickering. There we go, 0.12. I think that's about as good as I get. Okay, so we have that. All right. Check the distortion at the frequencies listed. Okay, so we can check the distortion. Percent distortion, 0.5. We are at 0.1. Okay, that's good, 0.12. Let's change the frequency. Yeah, very nice. It's at 0.11 here. 0.19. Oh yeah, we're getting really, really good. It's really good. All right, so you wanted to see that. It's right there. So it's 0.1137 total harmonic distortion. So that's good. All right. Okay, triangle DC level and phase range adjustment. Okay, we need to go back to the oscilloscope. Okay, we want to be on a multiplier of 4. Okay, we don't want to fix 10. Okay, pulse generator. Connect a pulse generator plus output through a coaxial cable to the 501 gate. Pull the 501 phase control out. Check that the display is several bursts of triangle waveforms and a horizontal bar connected to one burst to the next. Oh, I see. Okay. Put it on triangle function. And we need a pulse generator that's outputting square waves, 0.2 period, duration 0.1. All right, so gate in. All right, I'll bring the gate in. And amplitude, 0.2 volts. All right, square wave, amplitude, enter number 0.2 volts. All right, gets output here, and we are needing to turn on the control on. Okay, so we need to pull the phase knob out. Oh, there we go, something happened. Okay. Connect the pulse generator. Okay. Check the time base 0.1, duration 0.1 milliseconds. So 0.1 milliseconds is 10 kilohertz. Okay. And let's see, we have this gated on. And we're not getting any signal out. So we'll probably need an offset here. 2 volts. Oh, there we go. I needed an offset on my pulse generator. And we are now getting pulses. And let me slow the frequency down. There we go. Yeah, that looks right to me. Okay, so the pulse generator is gating the waveform, so we get these triangle waves gated by the pulse generator. So that is all working. Okay. Adjust if the operation is not described. Okay, adjust the output balance. Amplitude, clockwise in and out, 0.1, center of the trace, okay. Just output balance. Oscilloscope, okay, we gotta go back to this. Okay, we don't need this one anymore. We'll get rid of phasing. Center of the trace, okay, fine. And we look at the centered. Yeah, it's centered, so we don't need to adjust that one. All right, so we were looking good there. All right. Okay, procedure below. Okay, so triangle DC level, move the probe tip. What am I doing here? Below proceed. Oh, I don't need to do these. 5. Oh, okay. I think we are done. Yep. We are done. All right. Well, that took a while, didn't it? But we are fully calibrated now. And I can button it up. Take these BNCs out. Here's our machine. And get our side covers back on. Always worried about bending these. They're kind of flimsy. Let's see here. All right. Okay, so that is the function generator FG501. Good to a megahertz and does all kinds of things. So it's actually looks like it's pretty useful. A little bit low in frequency, but quite a useful little box.